All right, so we just completed talking about the basics behind integration and connecting that to it being the area under a curve, which is what one of the fundamental theorems of calculus is. So now what we want to do is get into this whole notion of how to actually apply the fact that the integral operation the is sort of like an inverse or the opposite of the derivative operation. Now what I have here is a nice little handwritten table and kind of tells us how to have a function and how to come up with its antiderivative. And so here you'll see I have some stars by some of the ones that we want to focus on. The first one here with the star just says that if we take a function that is a constant multiple of another function that we know, then its antiderivative, represented by big F of x, is just that constant times that antiderivative. And similarly here, for if we had two functions that we know of that are being added together and we wanted to take the integral or the antiderivative of that, then we would take the antiderivative of each of them and then add it up. Now this third one here tells us how to take the antiderivative of a power function. And this is specific for when our exponent here is not 1. So you'll see what happens here is that instead of how we do for the derivative, we would take the exponent and subtract 1 from it. Here we're going to add 1, and then whatever n plus 1 ends up being, we put that in the denominator. So that's how we integrate or get the antiderivative of a power function. Now, just to give you a quick example here, let's say we wanted to get the antiderivative of 4x cubed. Okay, so here we got the antiderivative of 4x cubed. What that would look like is we would say x to the 3 plus 1 power, all that divided by 3 plus 1. And we know that 3 plus 1 is just 4. And so now that will reduce to 1. And now what we have is x to the 4th. So x to the 4th would be the antiderivative of 4x cubed. And this makes sense because if we took the derivative of x to the 4th, we know that what we would get is just 4x cubed. So you can see why we call it the antiderivative now. Okay. Now, same thing with here, we see that for 1 over x, or x to the minus 1, the antiderivative of that is natural log of x. And we know that because the natural log of x, if we take the derivative of that, it just ends up being 1 over x. And for e to the x, and we'll probably see some of this later, but I want to go ahead and expose you to it now. For e to the x, we know that this is the only function where it tracks its own derivative. So it's a derivative of itself. So the derivative of e to the x is e to the x. So that means that the antiderivative of e to the x also has to be e to the x. Okay. And so now what we want to do is we want to take this particular chart here and we want to use it in an example. So I'm going to go ahead and clear this out and then we'll do an example here. Okay, so now let's say we want to take the following integral. All right, so let's say we have this function here and we want to figure out what the indefinite integral is here. And so the indefinite integral means that we're just trying to find a formula for the area under the curve for this particular function. We're not limiting ourselves from one x value to another x value of what the area under the curve would be. Okay. So here, if we simplify this, we'll see that this ends up being 4/5 x to the third plus 3/5 times 1 over x, and all of that times dx. And so this is the normal notation that we use here. And what this integral sign means, it is a theoretical thing that says, hey, if we're doing a summation of all those rectangles that we talked about, if we can do infinitely many of them, then we say this is the infinite sum. Okay, so that's what that integral notation is all about. All right, so back to the problem here. So using what we had from above, we could come here and single out our constant. And since we have two functions being added to one another, we can take the integral of each. So looking here, we have 4/5. We know for x cubed, we need to follow the power rule. So that would be x to the 3 plus 1 power over 3 plus 1 plus 3/5 times, we know that the antiderivative of 1 over x is natural log of x. And then here at the end, we put a plus c here. And what the plus c is there for is that we know that any function plus the constant, if you take the derivative of it, the constant is going to 0. And so unless we're given some specific conditions, or in this case, some x values to bound the area under the curve that we're talking about, then we know that several functions can end up being the integral or the antiderivative of our original function here. Okay, so if we did this function here and let's say we just added plus 1 to it at the end, so whatever our answer would be, rather, if we take that particular function and said this was 1, when we would take the derivative of all this, the constant part would just go away because the constant part is 0. We could change it to 3, we could make it negative pi, we can make it whatever. It really doesn't matter. Okay, this thing will still go to 0, and we'll still end up with this as our derivative. Okay, so to account for that, when we're going backwards, we say that this is going to be our antiderivative plus any constant. And so if we're given specific conditions here, or if we know a point on the graph of this particular function, then we could come up with specifics on what this constant actually should be. All right, so moving on to finish the problem here. Say this is 4/5 times x to the 4th over 4 plus 3/5 natural log of x plus c. And so we know that these reduce to 1. So now we have 1/5 x to the 4th plus 3/5 natural log of x plus c. And so here is our final answer. Next, we'll do an example where we have a definite integral, meaning that we're going to have the same type problem here, but we're going to have numbers here. And what that will symbolize is us trying to find the area under the curve of a function from one x value to another x value. Here, what we just did was find the area, find the formula for the area under the curve, and we didn't bound ourselves to any particular x values. So that would be the difference in between this problem and the next